for fun and profit. Okay. He's making coffee. Okay. So today's afternoon session is about using GPUs. And I'm using slides made from my collaborator, Tim Besart, at Marriott on GitHub, because I decided that they are excellent and I can't make anything better. So that's life. Well, yes. We will do a little bit of work in the terminal later on, just to show you that these things actually exist. Just GPUs, if you don't have a GPU in your laptop, Jupyter notebooks are kind of a pain anyway. So this tends to work better. Right, so we already, oh great, this formatting is wonderful. See, how big is the projector? Okay, anyway, always. So, yes. We already talked about what Julia is and why you should care, and you're still here, so you are still interested. The question is, what are actually GPUs? GPUs are hardware accelerators that are optimized for massively parallel applications. So think of it as, the comparison I always make is you have your CPU in your laptop is like a PhD student. It's really clever, but overworked, and can only really do one thing at once. But if you have a classroom of undergrads, you maybe need to give them very explicit instructions, but they all can work independently. So the idea is that GPU has very simple processors that that don't have fancy technology for doing out of order execution or like prefetching data as easily, but you have lots of them. And so you can hide a lot of this latency, of this slowdown that you get from using less intelligent processor units to get a lot of throughput. So if you have big data, matrix multiplication, anything like that, GPUs are wonderful. The goal for the project that began, oh gosh, I think, yeah, Tim started working on this in 2014. I started working on this in 2015. And over the last couple of years, we've built up an entire stack of libraries and a compiler toolchain that can translate high-level Julia into GPU code and execute it optimally. We are going to focus on NVIDIA GPUs because that tends to be what most people have, and that tends to be what most data centers run off. In the near future, this will change, or hopefully change a little bit. AMD is pushing forward into data centers, and Intel is also starting to develop GPUs and providing them. The entire technology is based on LLVM, like Julia itself, and you have optimized libraries and tools available for all of these GPUs. We also in Julia have the option to do actually TPU-based computation. So that's Google's hardware accelerator. And we have some support for OpenCL-based AMD GPUs, but that is not what we're going to talk about today. And it's been not updated recently. The goal is basically to say, okay, we're going to have an application and we want to perform some parallel operations. And for that, we do need to have CUDA kernels, which are programs that execute on the GPU. Traditionally speaking, you have your application in something like Fortran, Python, C++, R, Java, and then you have libraries that make it easy to write data parallel operations, OpenACC, Thrust, PyTorch, and then you have a low-level language that is C or C++ to write CUDA kernels. what we are proposing is, why not just use Julia for all of this? And the application level is the array abstraction. So you write with cuArrays, which implements a lot of these data parallel operations with the help of CUDA native, which is the compiler infrastructure. So we are separating the low-level infrastructure from the higher-level infrastructure. And most of you should probably only interact with cuArrays. But if you need to write your own CUDA kernels because you have a specific application, it doesn't quite work, you always can use CUDA native to do so as well. Yes, one question. It will crash, or not crash, it will throw you an error and tell you that it can't do that. So cuArrays are a representation of GPU memory. The CUDA native itself, if you ever looked at GitHub, you can you see these wonderful color bars, and this purple is the color of Julia. So this is a 96% of code is written in Julia for the entire compiler, which is pretty neat. We don't need to write any like low-level C++ and C to have a language compiled. We are compiling the same language in which we're writing our compiler. Okay. The first step you need to do, if you have a machine that has GPUs available, if you're on Tombow as an example, you can say add CUDA native, and then as usual you import it, and then you can write a GPU function. So this function is using GPU intrinsics, so it's only using thread ID X and qprintf. But if you're trying to execute this function, this kernel, on the CPU, it will not work. Maybe it will crash if you're unlucky. So this function is a GPU function. And the important bit is also that this is a kernel, and kernels in CUDA are executed asynchronously. Right? So you start an execution of a kernel, and then at a while later, you check back and you check back and ask whether or not the computation is done, because it's throughput optimized and not latency optimized. It's all asynchronously, and so you can't return a value from a kernel. Yeah. There is a notebook for lecture 4 in the directory, and it's the first one. Or did I not push this? Yeah, there's a link in the beginning of there. On the top of that, there are 2 links. Yes, I forgot to push it. Okay. Sorry about that. Let's come back. Yes, nice. Okay. The other important thing is that this code, right, is compiled as normally in Julia. So it's specialized code, and we can inspect that similarly to what we did yesterday with all the CPU code. We have a family of functions that are very similarly named. They only are prefixed with device code, and they will output all the device code being executed. And so we can ask, okay, which device code typed is executed when I'm running at CUDA say. And so this is getting the thread IDX from CUDA native and then using the base and intrinsic functions to do operations. I can also go a step further and look at what is this actually then an LLVM, similar to yesterday as well. And here we see the call to the LLVM intrinsic that gets us our thread ID. Who here has programmed GPUs before? Okay, for a couple of folks. So one of the things, if you look at, if this looks very foreign to you, the way to think about it is that we are doing parallel computation, and each thread on the GPU is executing this program in parallel. And so you need to know which thread is executing currently the kernel, which thread you are in order to get the right data. So a thread ID is basically which thread is currently executing the program if you think about it locally. Does it make sense? Right. It's the only way to differentiate between two data elements, right? Yes. Right. Normally you do some calculation on these indices in order to establish which data element you are supposed to be processing. And we then have, in this case, right, we're starting with 4 threads, so we're executing 4 threads in parallel. That's why we're getting 4 answers here. And then we can go a step lower and actually look at the assembly code for the GPU. And this is called SAS. And it's very tight and efficient code for what we're doing. I mean, we're not doing much, but I always forget what it stands for. It's shader assembly, and then I don't know what the double S stands for. One of them is for, yeah. I think it's shader assembly. If you want to learn more about how this works, there is a paper from 2017 on this that describes the entire compiler stack. That is up to your liking. Why do we want to actually run Julia code on the GPU? Like if you're used to Python or MATLAB, what you're doing if you're executing code on the GPU is you're executing libraries. Right? You have calls to matrix multiply, and those matrix multiply operations get executed. By being able to compile code, we are actually being able to make Julia abstractions work. And I will show a couple of examples in a second. First of all, the important question with all of GPU is it fast or is it slow? These are standardized benchmark, called the Rodinia benchmark set. And this is the speed up versus CUDA-C of the equivalent programs. So typically, if you're using a different compiler setup, you will see some variation here. But the important thing is that in general, we are competitive. There's some where we are quite a bit faster. We have a 22% speed up, and then other ones where are quite a bit slower. That is because of variations in compiler chain mostly, yeah. The what? The slowest one. I can show you the code later on. So, right, wait. So we can create a Q-array, as I mentioned earlier, and that is a representation of data on the GPU. And now we can apply any operation. So that op could be any function. And we use the thread ID to get the right element of the data that we want to do. And then we want to apply the operation to that element and store it back in the same location. And so we can write an abstraction. This is the apply abstraction, or other people would call it map, in which you take an anonymous function just provided by Julia, not a kernel, and you apply this anomalous function over the array. And so you're building up an abstraction. And so at the end, right, we are getting the result we wanted. We have squared every element. And so that's why we care about having a compiler, because if we didn't have a compiler for CUDA code, then this lambda, we would look at it and be like, we don't know what this does. This is just a function, a Julia function, right? And in traditional Julia, you just say map to that. And the whole Julia-based infrastructure for map, podcast, works on Q-arrays and automatically does this compilation. And again, we can look at the PTX code and we have our index calculation and we see, and there is no function call here, right? We are providing a kernel, a lambda, and then the kernel gets specialized on all the arguments, including the function that we are passing. So instead of having a function call, as you would just think you have, we actually see the inline function where we just do a multiply to do the square. Yeah, James? Yeah. So Q-arrays has bindings to all of the CUDA libraries. So, and then it's using Julia's multiple dispatch basically to interject and extend. Yeah, that just works. And that's what we're talking, right? That's basically the next thing to talk about is, okay, you now trust me, we have a compiler, we can do low-level stuff, we can write low-level kernels, we can inspect our code, but as a user, I would rather not write low-level code. I might actually just want to write array programs. And so Q-arrays provides an abstraction for high-level programming in GPUs. So you really shouldn't need to have any GPU programming experience, and we are providing a data parallel programming model. So yeah, operating over all elements in your array. Yeah. So the data transfer happens explicitly at the creation of a Q-array. So the Q-array only contains a device pointer. It's only the representation of the device side memory. So you're creating a copy on the GPU. Yeah. There are certain fallbacks that are in Q-arrays that will call into generic Julia fallbacks. And so you sometimes can see a slowdown. We have a facility to automatically check for that. But generally speaking, the goal is to never move your data automatically. You have to explicitly move your data, and then all operations on the data should happen on the GPU. So you just do a convert Q-array. So you have your input data, which is an array, and then you say convert to Q-array, and the reverse, you say convert to array from Q-array. And if you're used to like something like ArrayFire and Thrust, that is basically similar to what they provide. It's not OpenACC. So you're not writing for loops and then annotating them. So, right. In the simple world, we would just provide you an apply function or a map, and you can do this as we just basically discovered earlier. But Julia has already constructs for these operations, right? If you're used to Julia programming, you know how to use a map and you know how to use a reduce operation. And these also just work on Q-arrays. And then you can go and say, well, I want to broadcast a function over multiple Q-arrays. And and automatically get the podcast results. So podcasting, did you discuss it in Scopo? Okay. What podcasting basically is, if you have an array that has a dimension where the dimensionality is 1, or the length is 1 in that dimension, and you have another array that has an actual dimension there, it will expand along the axis. Yes. So my favorite demo of that kind is if we take A, it's a row, and A transpose is a column. And then we do dot times A. What should be the result? It's doing an element-wise multiplication, but it's expanding along each axis. You get the multiplication table. Because okay, it does the same thing for this. Because the dot star says element-wise. So right. So it is the same in this instance, but the meaning is different. It's the same because those are the rules of linear algebra. But for every operation, I can podcast it. Not every operation has these definitions. Yeah. Yes. So it's not comma 1 is the dimensionality, and the first dimension is just a row vector. And then in order to be a column vector, it needs to have 1 comma n. And that's the dimension. Wait, I did use podcast. Oh, so the dot is the shorthand for podcast. And the reason why we have the dot syntax is because it allows some neat optimizations. So if you have a long line of different podcasts, all of them get fused together, and you don't have any temporary allocations. Right. That is the step further. Basically, we can just call the podcast function, but then Julia allows us to also express this just as a dot syntax, avoiding all temporary arrays allocation in the middle. And that works for any function. So you can define your own function f, and say f dot podcast over arrays. And this podcast fusion is basically the same thing as saying, so why we like the dot syntax is it allows us to avoid temporaries, allows us to fuse things. And so you could just write f and you write it out and then say apply f over, or you could expand it, or you could use write f out and then say f dot, and then 2 times dot a, whatever you want, any crazy expression you put here forms a fully big tree, which then gets compiled down to a single kernel and stored in place with the dot equals. Dot equals means in place. The f dot means take this generic function f that I defined here and apply it element-wise over the output of this expression. In place equals mean that I will not allocate new memory for my output. I will use the memory of A to store the result. Yes. If you say A equals, it will say the binding A has a new memory location update, but A itself will not have changed. Yeah. Yes. Dot equals transpose, that will complain because the output of A is not in the same dimensions. Transposes are lazy, so they will be resolved. Oh yes, so we will So the issue there is that if in the case where A dot equals A transpose, the input memory and the output memory alias each other. So they're equals, right? The input memory and the memory we want to store in is the same. So we can't do in place. We need to create one copy. Yeah. Right. We copy the input once and then accumulate into the old input. Yeah. We have access to all the vendor libraries that CUDA comes with. So you can just call the QRAND library by using the normal Julia rand function, filling it. Matrix multiply goes to Q plus. We have access to QR decomposition. And then you can also use QFFT. And for deep learning, we have cuDNN wrapped, and all of these things are accessible and made available in a Julian API. Sparse linear algebra, if you care about that. Not all of these are completely done yet. It's a huge API surface, and sometimes it's mostly dependent on what people need. So if you care about, if you want to use some special things from QSparse and we don't have a wrapped, we welcome any help for that. So I told you what we have. Now let's talk a little bit about how you actually use this stuff. So this is a fun example where we basically are using a lot of different components from Julia and want to build up a very simple neural network. And the goal in the end is that we just have a normal Julia program and it works both on the CPU and on the GPU. So let's define our loss function, which is just our weights times our inputs, dot plus a bias, and then the predicted output, the training data, y, and then absolute square and the sum of that. And there's all just normal Julia functions, nothing special going on here. We have a way, and for brevity skip, but basically it's forward diff. We can get the gradient of our loss. And then we can write a very short training loop where we update the weights so that the loss gradient W is getting the loss with respect to the W and the loss dB is with respect to the bias. And then we have our learning rate and we update W and B in place in order to do gradient descent. And then we initialize this with some data. and then we run for 50 iterations our training loop. All of this is just CPU code, right? I haven't ever talked about what kind of array I'm putting here. The only time I'm actually creating arrays are down here, and these are all just normal arrays. In order to move this to the GPU, the only thing I need to change is x equals coarray of x, y equals coarray of y, w equals coarray of w. By moving my data to the GPU, I'm now using Julia's multiple dispatch to select the right methods that are implemented in coarrays to select coarrays, Q plus matrix multiply as an example. Yeah. It gives you an error at allocation time. And the GPU memory is garbage collected. So sometimes you do run into out of memory errors a little bit easier than you would on INC because you have less control. And that's it. They are updated in place. Oh, in the loop? Oh yeah, no, they are actually not updated in place. We could. The point is you don't have to. You can. So the point is you can actually go. So this comes from somebody who wanted basically wanted to do exactly this. This is a user contribution on Discourse, and they were like wondering how to do it, and then they came up with this code. Now we could go in and optimize this. Right? There are still optimization potentials here. Well, the important thing is that you can get prototyping and like start doing things very, very quickly. And as we kind of expect, since we're doing allocations, it's not as fast as it could be, but as soon as the data size becomes like interesting, the parallelism available on the GPU wins out over the CPU in performance numbers, and these are logarithmic scales here. Closer to 100, yes. Matrix multiply is the fastest thing. So the question really is, in some ways, So sometimes what happens if you do not use CUDA native properly, if you do not actually get to the point where you are calling optimized CUDA code, you get something like this, where you write your nice little code, and then you just pass it in, and you benchmark it, and you're like, oh, on the CPU it's so fast, and on the GPU it's, oh my god, it's so slow. Why is it so slow? And why is it allocating so much data? Any suspicions to what is happening here? Yes. It is actually each of these accesses. We never called add CUDA here. So we are not executing this on the GPU. This is just a doubly nested for loop. And it's a doubly nested for loop being executed on the host. And all of these accesses here are accesses over the PCI Express bus to GPU memory. So scalar iteration, that's what this is called, is very slow. Very, like, it's not even funny how slow it is. And that has to do with just how GPUs and CPUs talk to each other. So if we use coarrays that allow scalar folds, which is a global flag, which will turn off the capability to use scalar iteration. Why do we have scalar iteration in the first place? Well, we want to be able to run arbitrary code. Right? It's always better to have somebody's code working slowly than it having not working at all. So the access of GPU memory, so scalar iteration in general is the access of memory one after another. So I'm iterating over an array and I'm operating on each scalar individually. If I'm doing this way, I'm basically saying, right, for all of my elements, get the data from the GPU and then put it back onto the GPU. And all of this has to go over the memory bus, and that just takes forever. Yeah. Oh, and inbounds is one of these performance macros that we discussed briefly, I think, yesterday. Julia does bounce checking by default. So we check whether or not your array accesses are inbounds or out of bounds. And at inbounds just turns it off. It tells the compiler, I promise I'm good. Every axis, this axis, this axis, and this axis. So here, B is a Q array and A is a Q array. So the memory is on the GPU. But yes. Yes, it's very dumb. So you do it this way because you didn't know better. This is something that can happen quite sometimes if you're not careful because you're using a function that is using scalar iteration. Yes. Or in this case, you would actually want to, since you're doing something with offset accesses, you probably want to do write your own CUDA kernel, or you need to use a view and shift over your data once. That also works. And the nice thing about having this allow scalar is basically you can set it in your tests or at the beginning of your program and say, I want to make sure that all of my GPU code is fast. And then you get, on this call, you get an error which says scalar is disallowed. And you get a stack trace to which function is doing it. But really, the important bit is, right, we're doing an operation over this kernel. And so this kernel, we should actually be able to execute fairly, relatively quickly. One way of doing that is getting just rid of one loop and then operating over these ranges and using podcast. And then the podcast gets translated automatically to the GPU. So that would be a lot faster than our code before. But at each iteration here, we are starting a new kernel. And on the GPU in general, you want to avoid accessing memory multiple times. You want to avoid destroying the podium. And you want to avoid multiple kernels. So you want to fuse all of them together into one. So you could write this function also just by saying, give me a view over everything. And so I'm shifting things by views. And now that is quite fast. 93. Now it's as fast as the CPU. But what is the data size here? It's N64 squared times, yeah. I think if you would go a little bit bigger, the GPU would actually win out. Right. We can bump the problem size, we can go bigger. And then the GPU is winning out by 10x because we are actually using it. Right? The GPU is big. If you're only using a small problem of it, you're only using a small amount of the parallelism. So by increasing the problem size, you actually get into interesting territoriums. So modern data center GPUs have between 12 to 16, maybe if you're lucky, 32 gigabytes of RAM. Yeah. The other important thing to note is, right, remember when we talked about benchmarking, interpolation says execute this code first and then use its result within the benchmarking kernel. So we are moving the GPU data once. In this version, we are moving the GPU data every time, every benchmarking time. So here we are benchmarking just the kernel execution, whereas here we are benchmarking the time it takes to copy the data and execute the kernel. And copying the data is expensive. The B time is like at benchmark. It just gives you one answer instead of the whole statistics. The why we are doing all of this is like for the Climber project as an example. The Climber project is running on this infrastructure, and it allows them to write in a single productive programming language. They can use high-level abstractions. They can compose with other libraries easily, and they can choose to optimize the parts that they care about. I think that is another point. Once you start doing benchmarking, you can start looking at your individual kernels and then provide overloads for Q-array as an example to get speed up in specific regions of your program you care about. Composability, why? Is in some ways because we managed to separate the concerns very elegantly. We are separating your interest, you are caring about the operation of what you want to execute, what is computed. I care about where your data is. It's on the GPU. And I care about how I'm going to compute this. And by using an abstraction like map, if I would try to translate all for loops to GPU code, I would be bound by the semantics of a for loop. And the semantics of a for loop is iterate in order. I have given you no such guarantee about map. Map could execute in any order it chooses. And that's partly why we get away with saying, well, a map on a GPU executes everything in parallel. In total, this whole project is relatively small. The CUDA native compiler is about 2,500 lines of code. The GPU arrays .gl library, which provides a lot of the higher level infrastructure and feature set, it's a 1.5 lines of thousand lines of code. This is actually shared between different, potentially different GPU implementations. So CL arrays uses it, and if you're gonna add something for AMD or Intel, it's also gonna reuse the infrastructure there. And then Q-arrays itself, without all the libraries, is just like 900 lines of code. It's very small. I saw a wonderful tweet this morning where it was like 6 lines deleted, 7 lines added, 2 days of Haskell. Right. And earlier today, basically, I didn't tell you how we are calculating this W, the gradient for the W, and we are actually just using forward diff for that. So we are composing with generic libraries in the Julia ecosystem. The multiply is defined as a high-level API in Q-arrays. This is multiple dispatch working. And we have a generic matmul in Q-arrays as a fallback strategy so that we can actually support the arbitrary data types of Julia. Right? Q+ only knows about float64 and float32. But you have duals, you have measurements values, you have whatever you want. And so we have actually an implementation of generic matmul for Q-arrays as well. There's definitely more. We can also reuse infrastructure. With infrastructure, we mean other array libraries. One of those is distributed arrays. And this is my work. This is very much work in progress. Don't try this at home. This will probably not work out straight out of the box. Distributed arrays is a package that allows you to reason about data movement across multiple machines. And wouldn't it be nice if we could allocate GPU memory on multiple GPUs and then use it as if it was one? And so if you look at distributed arrays and you're distributing a normal array in Julia, you just get a D array with an element type and this array float64 underneath. And this tells you I've distributed the array across all the workers, and the underlying representation is arrayed float64. Now I can translate that by using map local parts. Can translate all the local representations to Q-arrays on the machine. And since I earlier set Q.native.device on each worker process, I set the device to be a different one. So if I have like 7 GPUs in my machine, I have 7 workers, each of them operating on a different device. And since I set this globally, all of these array allocations are going to different devices. And now I have my array striped across a 7 GPU machine. Yeah. Distribute takes setup arguments that describes the striping. We can talk about that offline afterwards, but distributed arrays allows you to describe all kinds of different partitions. And call what? We don't have a distributed FFT. Somebody in the back there is working on infrastructure to make it possible. Depends on your data size, as always. But if your data size becomes big, usual. Yes. One of the big supercomputers nowadays are basically just gigantic GPU machines. And if you have a problem size that is big enough for a supercomputer, you want to work on multiple GPUs. And then again, matrix multiply works. It is slower than if you would be only doing local data transforms, and there's a lot of overhead that we know about, and we know about how to get rid of. We just hadn't had time to get rid of the overhead. So this is very much work in progress and not ready for public consumption. But we are working toward this goal. Yeah. Yeah. Yes. So what you're doing is you're cycling in and out blocks of memory. So you're moving blocks of memory over the network. And then you're doing. James, you had a question? Yes. I mean, matrix multiply is a global operation. Matrix multiply. But for that, you need to move data across processes, right? And this is basically the story that we got to, where we got it to work. And like, yes, arrays will always be initially fast, right? Small input sizes, but as soon as the input size grows, once we go to 2 to the power of 16, we can no longer represent it on one GPU. And so while in the small use case, the distributed array has a 10x overhead, towards the end, that overhead vanishes, and we can continue scaling. It's doing the entire problem size. The entire problem was multiple 2 of these 16s, I think. I have to look at the setup again. Yeah. Good question. I can't tell you. I don't know. No, these are dozens of execution averaged. So yeah, I would be curious to find out as well. So if you ever do that investigation, let me know. Yes. So you can. So the CUDA driver exposes interfaces to do 3D, 2D allocation patterns, which we currently don't actually use. So that might be something to look into. We allocate linear memory. And so yeah, probably. But yeah, it's strange because in some ways you would be expecting the overhead to be. This was working with. No, not necessarily constant, because at some point you're saturating the GPU, and if you have a smaller, and if you go over that saturation, and each of your 4 GPUs is working in parallel, you have the potential to be faster. So right, we use 4 8 GPUs for this, which really that 4 8 GPUs are not faster than one is a little bit sad. But the point is that we can actually continue scaling. And there is a paper about this out. The other nice thing, right, is we're using Julia. It's Julia all the way down. And so sometimes, like in the case of forward diff, there are implementations that are for abstract array that are not as optimal, that are using scalar iteration. So the first time we ran our code, it was abysmally slow. What we can do, right? We don't want this. What we can do is we can either replace it with a podcast implementation, or we can go a step further and provide a specific override for QArray and say, for QArray, don't use podcast implementation because it's slightly less efficient. Use this kernel to do the calculation directly. So you can always choose after you did your performance analysis to say, hey, I care about this kernel. I will optimize it for my GPU, or I will optimize it for GPUs. And you don't lose any of the higher level features. You don't have to like call it. You just have an overload on the write function. So basically, if you want your code to easily run on GPUs, what we recommend is rewrite using array abstractions, so operations that operate over arrays and not in loops. Then in combination with generic code and using coarrays, you get GPUs for not free, but a lot less work. Avoid the anti-patterns we discussed. Use podcast expressions because they specialize nicely. And if you need it, write your own GPU kernels. And in order to figure out these parts, we have tools available. So reflection and introspection. I mentioned that earlier. We have device code, which tells you all the details you ever wanted to know. You can set the environment variable Julia debug for CUDA native, and then you get debug information about the kernel launch. So this kernel is being launched on optimized for the PTX version 3.5 with a shader model 3.5, and it's using 8 registers. And so if you're running a lot of kernels, you want to search for kernels that are using a lot of registers because they can't be executed as parallel as normal. And you get also information about whether or not it's using shared memory, constant memory, or local memory. One important thing is, and I see this going wrong all the time, is in order to properly measure performance, since the GPU is executing your code asynchronously, you can't just benchmark the function call to identity.x, because it will be executed asynchronously. Until somebody looks at the memory, nobody has, the code does not have to be executed. So if you just benchmark this, you're only benchmarking how long it takes to launch a kernel. So GPUs are 10,000 times faster than my CPU code. No. A kernel launch is 10,000 times faster than your CPU code. Yes, that is true. So the coarrays has an add-sync macro that makes sure that the kernel launch that is happening here is synchronized. And then you get real numbers. We also have a time macro that instead of just looking at CPU allocations, also looks at GPU allocations. So if any GPU allocations are happening, those will be reported, and that's also very helpful to look for. And then we have more specific, where you just want to know how long it took at time. I don't want to know anything about garbage collection time. And basically, we have measurement metrics. Use measurement measure before you optimize anything. If you didn't measure and you optimize, you're not doing anything. It's like doing a scientific experiment and not knowing your baseline. How do you know that you actually did anything? We interact with the NVIDIA profiling tools. So you can just say nvprof, and then you run your Julia code. And we also allow you to ignore all the startup costs that we have. So profile from start off. And then you can say add CUDA driver profile, and it will only profile this execution. And so you get a very tight profile instead of having 7 seconds of empty space. You can also use NVVP and actually get a graphical interface and look at the time it took. This is memory allocation. These are driver API calls. And then you have your singular kernel execution. And it's using 100% of compute, which is very nice. And generally, in some ways, here, what the issue is, we are not doing enough compute. We're spending way too much time we're spending more time launching kernels than we're doing actually any execution. So this is not a type profile. You want to get into a world where you're actually doing operations that are kind of heavy, like sign. Is heavier than just doing the identity operation. The identity operation just loads memory and stores memory. You get down to instruction level or function level profiling information. That's all integrated. And in general, for me and from what I've seen with other people, there are still rough edges as usual with anything that is research code. This has been in the work for a long time, but it's still research code in the end. We put a lot of work into engineering as well, Tim especially. And you have high-level tools, you have low-level tools, you can use them. You get single language GPU programming, which is actually exciting. It's like, don't have to write 300 lines of CUDA setup calls. The weakness is, in some sense, Julia is a language that is too powerful. A lot of the GPU, a lot of the things that Julia can do don't work on the GPU. So you can't write to a file from the GPU. You can do memory allocations on the GPU, but the memory allocation on the GPU is very slow. We don't know yet how to do generic function calls. So code that is type unstable will not run on the GPU. We do have some issues with using generic functions that are written for the CPU. Like there are, I think, Sign used to be a case that was written in that was calling OpenLibM, a math library from highly optimized C code. But since you're calling into a into a CPU library, the GPU code would be like, yeah, I can't do this. And so we are working on a method to replace functions at these core boundaries. We have a very active community on Slack and Discourse, also for the GPU stuff. So come and hang out if you have questions, basically. Yeah. And now I have a little bit of time, and we can actually like run some of this code. Yeah, let's take a break. The one thing I wanted to quickly show you guys, and then we can actually go, I think, into the starting to work on your projects, is how do you use all of this stuff on the OIST infrastructure? I only got access to Tombow, and Julia is only installed on Tombow. So right now, we're here. Yes, you just complain. Just the good thing is if you're telling your IT that you want something, then they know that they have users, and then they actually care about it. So we load Julia. We also want to load CUDA. And then, because for other reasons, we need to load a specific version of cuDNN. cuDNN, which is the NVIDIA's deep neural network library. Then we can use srun to get an allocation on a GPU partition. And I'm requesting one GPU. I'm starting a bash to have an interactive session. And now I'm on a GPU machine here. And so the first thing I always do is to check what kind of GPUs do I have. I have old GPUs. It's very sad. I wanted to have fun GPUs. Anyway. Yes. And then I start Julia. Yay. And once I have my Julia going, like the only thing I ever did here was to add CUDA native and cuArrays, right? That's just add CUDA native, cuArrays. Shouldn't do anything because I already did it. Yes, so the issue is network drives. Anything on a cluster is often on a network drive, and any operation with Git on network drives is slow. Also that. Tombow is lovely. I remember it fondly from my internship, and afterward it was no longer useful. Oh, no, don't. Thomas. No worries. And now we can start and say, well, I want a cuArray. Oh, that is not working. Sorry. Yes, why is this so fast? So fast. I thought of you. The hardest thing about clusters is getting the commands right to do anything. No, I like Slurm. It's much better than SGE, Sun Grid Engine. Is there anything in particular you want to see, like as proof of concept that it actually works? That probably means at this point there are only like 4 GPUs, and if I got one, somebody else got one. That's the least developed part of the API, so congratulations to that. Sybil filter, yes. I mean, that's just a convolution. No, I don't want to sponsor. Right, so and then how do I get a sparse array? Ah, nice. Okay. So right, Julia has a sparse array, which is a standard library. And as part of that, I can get a randomly sparse array, let's say 25 or 1024. And I think this was the sparsity pattern probably. Yeah, so right, I get about 20% filling randomly. And then I can have a Q. I have a Q sparse vector. And I can take my aspirand and this the first thing. Oh, fun. Okay. That is the first issue. See, that's why I like taking random input. That's just literally what I did. It's like, well, you can also just open my GitHub issue. If we don't display it, it's fine. Yeah, it's a displaying logic that is broken apparently. And now what do I do with sparse vectors? Okay. Ah, interesting. Okay. So does things like this work? That would be important. No. Fabulous. Oh no, this is displaying it, isn't it? No, that's. I mean, there are things I can definitely do with it because we have tests for it. Conversion. And can get Choleskis of matrices. Fun. Yes, they did. Yeah, I mean, so buyer beware. Caveat emptor. There is one person I know of who is interested in sparse stuff on the GPU, and she has only occasionally time. So if you're interested, there are opportunities to be done. Well, right, let's And now I can just say add inbounds. I think I like typos. Right, so now I'm just writing a kernel directly, and since I'm not very creative, I have users for that. Users are very creative. They come up with things. Right. Well, this is just a function that does a vector addition, and now we can allocate a couple of arrays. We have out equals q array under 2024. I thought we fixed that. Ah. So one of the other things to keep in mind is that GPUs are much better at operating with float32 than they are with float64. On proper server class GPUs, you don't have a big penalty. It's just 2x, so what you would expect. But if you're running on consumer GPUs, float32 is a factor of 32x faster because they want you to pay more money. It was this. Yes, I didn't have a type. No. We are very literal. This will be an array of float64. It will be float64 on the GPU because you told us that they wanted float64 on the GPU. Right, there are use cases for all of these situations, and I can also do things that are slightly silly, like create a float16. Float8 doesn't exist. That makes very little sense. Sadly, float128 we don't have create support for. And then A, we can just take some data. Compiling code is fun. And then we create more data like that. And then we do add CUDA and we say threads. And this threads can be, if you're doing a multidimensional launch, it can be a tuple. So it could be, in this case, it would be 2024-1-1. But if you're doing something more complicated, you have full access to the threads and blocks launch size. So this blocks is the same definition. And so if you need that for your CUDA application, you can specify however you want to do your launch. You have also access to shared memory and stuff like that. Yes. I called it VAdd. Oh. This is a moment where the chat like really shines. And since A and B were both 1 to 2024, we now have 2. We multiplied everything. And add CUDA, add device code Ah. And so this is the code we actually generate through LLVM for the kernel execution for PTX. So PTX is the intermediate representation that NVIDIA uses before they then give this to the assembler and assemble and run it. And as I said earlier, since we have A dot times A transpose. Yes, it compiles to the representation shared used by the CUDA compiler. So it doesn't compile to CUDA C. Mm-hmm. It supports everything up to 10. The lowest version of GPUs we support is shader model 35. So very old GPUs don't work. Yes, but sometimes people have them still in their laptop. Yeah, you can do warp shuffles. So this is actually one of the fun parts. So sometimes we don't have the operations wrapped yet, just because we didn't get to it yet. But it's so as an example, what's currently not wrapped is the on the Turing architecture you have a matrix multiply that is operating in float 16 and accumulating in float 32. The hardware instruction for those we have not wrapped yet, because we haven't come up with a very good interface for it, but it's doable. It's not technically impossible. So as an example, we have in CUDA native, we have the compiler code, and then we have the device library. This device library includes all the information that we have, as an example, like how to handle arrays on the device. We have a cuDevice array, which represents on the device the CUDA pointer and has the shape information necessary to fulfill the semantics that Julia would expect of a device. So you can create a view of a cuDevice array on the GPU. But we also have the CUDA library, which basically, right, you asked for the warp operation, so we have warp shuffle. And we wrap all of these through. This one is wrapped through calling assembly, because probably LLVM wasn't exposing it well. Where's the warp vote? It's also sometimes you have to use assembly because it's not exposed well. But generally, it's easier than that. What did I recently add? So all the NVIDIA provided functions for doing math operations on float 32 and float 64, as an example. We have to wrap them so that you can get optimal speed and access to them. And so you can say CUDA native .cos and get this version instead of the Julia version. We are using the LLVM CUDA toolchain. So LLVM supports NVPTX as a backend. And so we retarget the code produced by Julia. So the Julia compiler is producing LLVM-IR. That LLVM-IR is produced for the CPU. And so as part of our compiler, we actually go and we have the intermediate representation generation, which is basically getting the information out of Julia, loading it into LLVM, and then we start doing some transforms on it to make it amendable to GPU and to mark things as kernel invocation, to replace exceptions with stack traces embedding so that we get actual stack traces on the GPU if you ask for it. So that's actually maybe a fun example to do. Let's go back to my VecAd example and remove this inbounds. And what happens in Julia if I now say, if I would say 1025 here? What is your expectation? Well, let me be blunt. Right. Where would the error come from? Where would the error come from? Right, index out of bounds should normally throw an error. Oh, this is, it compiles correctly. Right. So now we are getting actually an error. Oh, okay, this was too big. Can only launch kernels that are a certain size. So let's do the I thought. Okay. I thought you can have 16,000 on the X index, but only 1024 on the Y index. Yes. So out. Let's define an N. Let's define that N to be 256. Let's define our A 1 to N. Yes, the A is already GPU memory, so I can actually use NVIDIA SMI, and it tells me that there is a process on the GPU, and it's using about 75 megabytes. So no problem, because we didn't trigger a memory sec fault. What? Wait, that makes, oh. What did I say about CUDA being asynchronous? It's always asynchronous. So we get the error message 1 CUDA call delayed. And we are getting quite a few exceptions because we're having 1024 out of bounds. And it's telling us an exception was thrown during the kernel execution. But since we are optimizing for speed first, we don't know which exception. We are not able to provide you a stack trace. But you can run Julia on debug level 2 for the getting device stack traces. So we can restart Julia and say Julia dash G2. Do the same thing. And now we are producing less optimal code because we are valuing the debug information more then we are valuing performance. And need our out, wieder an A. Oh, this was the wrong out. And now whee! Since we're having so many, we are having 256 threads going out of bounds. Our stack trace printing we should be able to do that better. So I'm going up. So stack trace. Why is this stack traces? Okay, stack traces. And now I have to go back down and says, okay, so the second one is a check bounce. The third one is the line number. Then we have a throw bounce error. Oh, good question. Get index, check bounce. Oh, because it's 256 and it's executing one chunk and then a second chunk, and then the second chunk triggers the error again. Well, I came up with the idea to do this much out of bounds was crazy. But at the end, we get to actually the precise line where the out of bounds access happens. Line 3 in the repo. So 1, 2, 3. Okay. Any questions about GPUs? Okay. Not yet, but we would like to. And what? Pin memory, yes. With texture memory, we have not webbed yet, but we had multiple requests, and so probably doing that at some point soon. Also, good first PR. Yes, yes. So if you really care about GPU performance and you want to get the last 10, 15% out of your GPU, you actually need to be knowledgeable about the precise architecture you're targeting. Yes. So right, as I started yesterday saying, our goal is not to be as fast as C everywhere. Our goal is to be much more usable and within 2x, and that's we can easily provide. If you have the know-how and if you have the knowledge of how to actually program GPUs, you can get the same performance, but it's the same amount of work, and you need to do the same tricks that you would do in C. There was yeah. Well, the amount of work, Anko, your bass is carrying very far. So how much more work? Well, I think I recently looked it up, and the first email on the mailing list about CUDA support happened sometime in 2014, with Tim basically going, I witnessed backend for CUDA and Julia. This is it. I hope people can use it because I don't have time to continue developing this. I have to finish my PhD. I read that, and then I started over Christmas to take chunks of it and import it into base and add features. So the Julia compiler at the beginning was not ready to be retargeted very easily, and there was a lot of debate of the question is, should the Julia compiler have the capability of targeting CUDA, or should we strive to be flexible enough so that it can, but the functionality can be implemented as an outside package. And so in the end, we decided to make sure that what the Julia compiler produces is flexible enough, and we have certain hooks, certain options to set to change the output slightly to make it easier for us to actually do the retargeting. And then it took I would say nearly a year and a half or so to get from this C prototype with Tim working almost full time on it. He ended up doing his whole PhD about Julia and GPUs and CUDA. And we spent 4 months in Boston working on the compiler infrastructure while I was here at OIST. And then and so we've been working on this for 4 years, 5 years now. It's now getting to the point, similar with Julia. Julia in the beginning was pre 1.0. Lots of things were changing rapidly. It was not necessarily the best language to build a long-term project on because things changed. Now things are no longer changing as quickly. That also allowed us to spend less time catching up to the Julia core compiler with the GPU compiler and just stabilize and add features. So depending on how you're counting, it's a couple of years, but once you do it once, the issue is not necessarily writing a compiler again, it's more writing a runtime library. So if I'm going out and say I want to target AMD, we have an AMD compiler. It's an early prototype stage, but it works. But we don't have a runtime library to the same extent that the CUDA stack has. So that's the next hurdle to overcome, and that's just a lot of engineering time. Cool. Then I would say we can take a 10-minute break and then continue working on your projects.